Okay, how's everyone doing? Ooh, that's loud. All right, so you might notice I'm not your regular professor, but I am a regular professor. So I'm Mike Franklin. I'm the other database professor here at Berkeley, and also spend more of my time these days being chair of the CS division. So if you have questions about what's going on with CS and EECS, we can talk about those towards the end of the class. But Professor Hellestein asked me to fill in today. He had to be off at an event, and so I'm a little rusty with this stuff. But if you guys help me, we should be able to get through it. So my understanding is that you guys have started going into SQL in some detail during the last class, and you actually got pretty far along the notes. And what I wanted to do today is just kind of wrap up. See if I don't. If I want to just wrap up the SQL part of the lectures, and I believe you guys have a homework that you're going to be doing in SQL, and we'll just go from there. So, all right. So you guys went through sort of the basic, select from where, and some more advanced aspects of that. And there were sort of two main topics left that we want to cover, at least give you guys a chance to see. So the first one is something called constraints, which, if you remember, SQL has really two languages, the DML, which is the data manipulation language, and the DDL, which is a data definition language. And the DDL is how you describe what the database should look like. So you describe your tables and your indexes and things like that. One of the other things that's really powerful about the DDL is you get to describe rules about the data that all instances of the database have to conform to, forever. Okay, so not only do you say that, I have in my database a students table, and students have, names and student IDs and addresses and so on. You also get to say that, the same student can't be in the database twice, and other statements of truth like that. And it turns out that this is a really important concept in databases. A lot of people miss this, but the fact that you get to encode those rules into the actual design of the database is really important, because if you weren't able to do that, you would have to write it into the logic of every program that touches the database. Okay, and that just as a software engineering, from a software engineering point of view, is just a nightmare, right? Because not only do you have to remember what all the rules are when you're writing your programs, but people you've never even met who are going to come by after you've long, been fired or moved up to being CEO or whatever happened to you, they're going to come along and try to write programs against the database. And if they don't know what the rules are, they could easily write a program that could corrupt the database. Okay, so by encoding these constraints into the definition, using the DDL into the definition of the database, they're preserved for all time. And so when somebody else comes up and writes a program that does something, tries to insert some data, if that data would violate a constraint, the system will say, "Oh, sorry, you can't do that." Okay, because that's going to corrupt the database. Okay, so it's a very, very powerful concept. So I think you started on this last time, so I'll go quickly. But the idea is they're called integrity constraints. Sorry, and let's see if this thing works. And, again, the idea is you're not allowed to do an operation that would cause a constraint to be violated. And so, obviously, if you're just querying things, that's not a problem. You can't corrupt the database by querying it in any good database system. So it's really just when you're modifying the database. So when you're inserting new records, you're deleting old records, and you're updating existing records. The system can check to say, hey, wait a minute, is that update going to violate some constraint? Is that going to cause something that shouldn't be allowed in the database to be in the database? And so there's a whole bunch of integrity constraints. We're only touching on them briefly. But there are things like domain constraints. So you've already been using these, you just didn't realize. So when you say that student ID is an integer, okay, that's a constraint. If somebody tries to create a student record where the student ID has characters in it, has letters in it, the system will say, sorry, that's not a valid student ID. Okay? When you are at a website and you're filling in some form and it says, and you leave something blank, and you hit submit, and the page returns and says, sorry, you have to fill in these fields, those are integrity constraints. Whoever created that database said, I don't want to insert records that don't have this person's email address in them because then I won't know how to spam them. Right? It's not necessarily the most uplifting example, but it's one that you see all the time. Right? So, domain constraints. Primary key constraints we'll talk about. Foreign key constraints, a little more advanced, we'll talk about those. And the sort of just general constraints, things like, we'll look at some. Okay? So domain constraints you've already done. Those are fields have to be of the right type, so that's just a type definition. And we'll do primary keys and foreign keys in a second. So I've already said this, but I just want to emphasize it. The whole point of constraints is to reflect, things that you want to be true about the data that gets stored in the database. So the next topic you guys are going to study after you do SQL is database design, where it's kind of a fun, but it's a fun process where you take some real-world entity that you're trying to model, whether it's a university or a social network or a physical transportation network or whatever, and you try to figure out, okay, if I wanted to represent everything that I needed to know about that entity in a relational database, what would be the right set of tables, what would be the right set of fields in those tables, and so on. So that's called database design. When you're designing the database, that's also when you start putting in these constraints. Okay? So constraints aren't an output of a query or looking at the database, but they're actually the inputs. They're the inputs about things that you know in the real world that should be true, that you want to make sure any legal state of the database at any time guarantees that those things are all true. Okay? So, if somebody hands you a bunch of data, you could look at it and check to see if the constraints were true. But what you can't do is look at an existing set of data and then with absolute certainty say, okay, here are the rules that I know, here are all the integrity constraints that I know are true for all time. Okay, because you might look at an existing state of the database and say, oh, well, there aren't any duplicate student IDs, so maybe there's a constraint that says no two students are allowed to have the same student ID. That would be a lucky guess, because you might also look in that same database and see that no two students have the same address. Okay, so then you might end up saying, oh, well, I've got another integrity constraint. No two students can be at the same address. Well, that would have been a bad guess. And eventually, somebody will try to insert a legal record of a student that lives in the same address as another student, and it'll throw an exception. So the whole point about integrity constraints is they're not tied to any one kind of state of the database at any time. They're supposed to be true over all time. Okay, and that's just keep that in mind. I've said it 3 times, but that's because it's important. All right, so let's look at one that you've probably already been playing with a little bit, the idea of a key. Okay, so keys are really used for 2 things in database systems. So there's this idea of a unique key, okay, or sometimes called a primary key, but it's a little more subtle than that. But the idea is that there's a field or a set of fields that uniquely identify every record in a particular table. Okay, so I already gave one example, like student ID. Given a student ID, that student ID will identify at most one student in the table. Okay, so it's a unique ID. And you're faced with this all the time, right? You're always forced to create usernames, right? Usernames, if you type in a username that already exists, the system complains. It says, sorry, that username's already taken. Well, why is that? Well, because if the system wants to send a message to somebody with that username, and there's 2 people with the same username, things don't work correctly. So there's a key constraint in whatever underlying database system there is. It says usernames have to be unique. So that's one use of a key. Now, given that you can uniquely identify any record in the database using its unique key, using its primary key, that also lets you do pointers so that you can refer from one table to another table, right? So you can refer from records in one table to records in another table and do that safely. Okay, so really unique keys, these primary keys do two things. They guarantee uniqueness, and then given that uniqueness, they basically serve as logical addresses for records. So you can always find a record given its primary key. So here's an example from the from the university database. You've got students, and you have their ID and name and so on, and then you have these enrollment records, right? This is a transcript, right? This says the student with SID, 53666, took the course, which I think is one of the few courses we don't offer at Berkeley, Carnatic 101, whatever that ID is, and they got a grade in C, which, that sounds like it might be a hard class, so maybe that wasn't such a bad grade. But that's what this enrolled record is telling you, okay? And so if you want to understand that, well, it's saying that the student whose primary key whose SID or primary key is 5366, is the student that's being talked about in this record. And this record here, right, is talking about a completely different student. Okay? So on the student side of thing, those SIDs are going to have to be unique. They're primary keys. They've got to be unique. And the one over here, the thing that's in a different table that refers back to that primary table, that's called a foreign key. Okay, and so we'll see how you specify this in the DDL, but basically what you would say is SID enrolled is a foreign key referencing SID in students. Okay, so that's how you do that connection. All right, so some definitions. These are a little irritating, but they're good to keep straight. So there's a definition of a term called a superkey. So a set of fields is a superkey if no two distinct tuples can have the same values for all the key fields. Right? So if I have students that have SIDs and name, okay, then and I know that SIDs have to be unique. So SID is a superkey, right? No two different tuples can have the same value for SID. No two student tuples can have the same value for SID. Turns out that given that, no two students can have the same value for the combination of SID and name, or the same combination of SID and major. Right, or the combination of SID, name, and major. Those are all superkeys. So a superkey is somehow, potentially bigger than what you need for uniqueness. So that's a superkey. So any set of keys, any set of fields that are guaranteed to be unique are called a superkey. And a set of fields is a key for a relation if it's minimal. So we're going to use the term key more specifically here. So that means it's a superkey, right? Uniquely identifies every record in the table. But if you took away one of the fields, it wouldn't be a key anymore. It wouldn't be a superkey anymore. Okay, it wouldn't uniquely identify the record. So, for example, did I say that backwards? Yeah, I said it backwards. I haven't done this for a while. Sorry. Let me start again. So, superkey uniquely identifies records in the table. Keys, without the super, are things that if you that no subset of those fields is itself a superkey. So take the example again of SID and name. Okay, if I take away the name from that, it's still a superkey, right? SID still uniquely identifies all the students in the student table. So the combination of student and name is not a key. It's a superkey, but it's not a key. Okay, because it's not minimal. So that's all that is. And then, of course, it may turn out to be that you have multiple keys for a relation. Okay, so you might have somebody's student ID, and you might have a sample of their DNA, okay, or their thumbprint or something, right? Those are all things that could be unique to that person. So those are all keys. If they're all minimal, they're all keys. And so what you do is you sort of arbitrarily pick one to say, okay, the primary key is going to be this one. So, if you had your choice between SID and DNA, you'd probably pick SID because it's a lot shorter. And if you're going to be using it as a foreign key, you're going to be storing it all over the database. But, it's up to you. You could store you could use the DNA as a key if you wanted. Okay, so you as the database administrator pick one to be the primary key, and all the rest of them are called candidate keys. Okay, so this example here is just, as we've said, student ID is a key for students, right? It's arbitrary. We force that to happen by the way we assign student IDs. Name, is that likely to be a key? Just the person's name. Absolutely, not. We have a lot of students who have the same name, so it's not a good key. It's not a key or a super key. The combination of SID and GPA is a super key, okay, because it's going to uniquely identify any student, right? Because just having the SID is enough to identify an individual student, and so SID GPA is a super key, but it's not a key. It's not a minimal key. All right, so a lot of definitions, but just, wanted to go through it. Any questions about any of that? Okay, so then the question is, all right, given these concepts, how do I use them when I'm creating my tables? So the way it works is in SQL, you can say that one field or set of fields is the primary key, okay? But if you want to enforce the uniqueness constraint, right, which is the other thing, remember, keys have two uses. One is to be able to point at records, and we're going to use the primary key for that. And then the other is just to say that field or set of fields has to be unique in the table. Those are candidate keys, and the way you do that in SQL is by saying unique, okay? So you have both of those options: primary key, which ends up being sort of the identifier for the record, and then uniqueness constraints that just say, hey, this field or set of fields has to be unique. If somebody tries to insert a new record that has a value that is already in this table for these fields, you can't insert it. That's what unique says. And so this is kind of a little bit of a silly example to show that you got to think a little bit when you're trying to decide what's your primary key and what's your uniqueness, what are your candidate keys. So here's two enrollment tables, enrollment 1 and enrollment 2. They've got students who are referenced by their IDs, courses referenced by their IDs, and the grade. So this says, when this student took this course, they got this grade, okay? And the question is, what do I want the primary key to be there? So enrolled 1 says, all right, the primary key is going to be the combination of student ID and course ID, okay? And table 2, enrolled 2 says, well, no, it's okay. The primary key is just going to be SID. So the only thing, the primary key is going to be SID. But I want to make sure that the combination of CID and grade in the database is unique in this table. So we got to sort of parse through what these mean. Now, presumably, if you were designing this database, this is what you'd want to happen. You'd want to say, for a given student in course, you only get one grade. Okay, is everyone happy with that as a constraint? Like if you were building the database for Berkeley, is that a reasonable constraint? Right? Every student, for a given student in course, you only get one. Can only be one grade. What does that mean in practice? Anyone want to help me out here? It's lonely up here. Yeah, please. Yeah, right. So it means you only get sort of one official grade. You're only allowed to take a class for an official grade once. Okay, so it's probably actually not the way the Berkeley database is designed. Not that any of you guys would know this, but if you get a low enough grade, you're allowed to repeat the class. This wouldn't let you do that. This constraint would say, sorry, you got a D minus. Well, that's the grade you're going to get in that course. Okay, so that's what I'm talking about when I'm saying that these constraints, encode sort of what truths about the world, right? This constraint here, if we can implement it correctly, encodes this truth that actually might not be accurate. It may not let us do what we want to do. If you want to allow people to take courses multiple times and get different grades, then this constraint won't let you do that. You won't be able to record that in the database. Okay, so that's good to see. All right. But anyway, let's assume that we've decided this is the rule. Okay, you only get to take a course once, or at least you only get to take a course once and get a grade for it. So how do we implement that? Which of these two schemas implements that constraint? So I think there's an animation here. Oh, okay. Well, let's look. So let's start with enrolled one. So we're going to start inserting new records into enrolled one. So this says student 1234 took this wonderful class CS 186, and hey, they got an A+. Great. Okay. Now, so that gets into the database. Now, insert into enrolled one. The student 1234 took CS 186, and they got an F. Is that insert going to be allowed? Not in enrolled one, because enrolled one says the combination of SID and CID has to be unique, and you can see that these two have the same value for SID, CID. Okay? So in enrolled one, you're not allowed to do that. Okay, but then if student 1234 takes another course, say 61C, they kind of went backwards here, but they got an A+. They got an A+ there. Okay, that one's allowed. Okay, so that's what's happening with these inserts in enrolled one. Okay, so does it look like enrolled one, this primary key specification, is encoding this constraint? Looks like it is, right? It's saying that for any given student, any given course, at most one grade. That means when you try to insert the second grade for 1, 2, 3, 4 taking this class, they can't do it. All right, so that's enrolled one. What was enrolled two? Before we look at an example there, does anyone think that enrolled two, encodes this correctly? Does it look like it does? Anyone want to guess what the key constraints in enrolled two are doing, what they say? So primary key is SID. Primary key has to be unique. So what does that mean? Yep. Yeah, it's the best university ever, right? Each student only can take one class, right? Each SID is only allowed to be in this enrollment table once, because the second class they take, you try to insert that record, it won't allow it. So, let's try that. So 1, 2, 3, 4 took 186, that's fine. 1, 2, 3, 4 took 186 again. That's not fine not because of this, because we're over here. It's not allowed because we already have a record with SID 1, 2, 3, 4 in the enrolled 2 table. Okay, so that won't allow that. Okay, which is a good thing, but unfortunately, it won't even allow this one here, which says that same student took 61C and got an A+. You can't add that record because there's already a record for that with that SID in the table. Okay, so clearly this is not doing what we wanted to do. Now there was this question about whether this is really the right thing to do, but assuming it is, the left-hand enrolled one looks like the correct implementation, and enrolled two is not a correct implementation. Okay, and then what about this last record into enrolled two? Is that allowed or not? So some other student took 186 and got an A+. Is that one going to be allowed? Too easy? All right. Well, let's see. We have a uniqueness constraint on the combination of CID and grade. So that means no two records can have the same values for CID and grade. So if you kind of look through this, we already have a 186 with an A+ here. So when we try to insert this one, the system will say, sorry, that's a duplicate record. It's not allowed. It violates this uniqueness constraint. Okay? So this would make... this design would make a lot of people unhappy. It would make student 1, 2, 3, 4 happy because they don't get to record their credit for 61C. And then it makes this person happy who doesn't even know who student 1, 2, 3, 4 is, but they can't get their credit for their course because it just so happened that this other student took the same course and got the same grade. Okay? Yeah, please.
So that statement saying unique in the two CID grade. CID and grade are independently unique, not unique as like a...
They're unique the combination of them is unique. So you're allowed to have, so that uniqueness constraint, it's an important point, and I'm probably saying it wrong. That uniqueness constraint says the combination of CID and grade has to be unique. But you can have multiple records with the same CID as long as they've got, I'm sorry, I'm pointing in the wrong place. The same CID as long as they have different grades, okay? And you can have multiple records with the same grade as long as they have different CIDs, but it's that combination. It's that whole set. Okay, so that's a really important point, is that when we talk about keys in a relational database, it can be a set, it can be an individual key or a set of keys, right? And in this case, the primary key is the set of these two keys, SID and CID, and in this case, the primary key is just the single column SID. Okay? All right, so anyway. So I guess what this says, this is the definition of Enrolled 2. It says students can take only one course and no two students in a course can receive the same grade, right? Which is really probably not a very good database design, okay? But this is kind of the fundamental idea of this whole topic, which is these constraints really determine the meaning of your database. They determine the semantics. They determine how well this thing you're designing models the real world. And if you get it wrong, really irritating things happen. So I think you can trace back, like when you go to a website and you're trying to type something in and it's not letting you for some reason that you can't understand, more often than not, it's some problem like this underneath, that they have a constraint on their database which is just not correct, and it's causing you to not be able to enter your data. Okay? All right, so that was primary keys. The other use of keys, again, is to use as targets of pointers, and that's called foreign keys. Okay, so a foreign key is a logical pointer. It doesn't point to the record, on disk or in memory, but it says, hey, this record over here refers to this record over here. Okay, and because I have a unique key on the records over here, I know that any one value from this record will map to at most one value over in this other table. Okay, and if you want to be more careful than that, you can make sure that every record in this table refers to exactly one record of this other table. Okay, so I said at most one. Okay, but if that's not what you want, you might want exactly one. That's called referential integrity. So you can't have dangling references. So here's our example again, enrollments and students. And now if you look at the enrolled table, we went with that better design, right, that the primary key is SID and CID. Okay, but then we're saying a little bit more. We're saying that, hey, by the way, in this enrolled table, this field here, SID, that's actually a foreign key. That's actually a reference to the primary key of this other table, students. Okay, so what that means is that when I try to create a new record in enrollment, I said, hey, let's say somebody hacked into the system, and they said, hey, I want to, mess with the enrollment table for some reason. They try to insert a new record that has some student ID. Okay, the system's going to look up and it's going to say, hey, wait a minute, 11111. There's no student with that ID, so that's not allowed. That's not a legal update to the enrollment table. Okay, so that's what a foreign key does. So that's not going to be allowed. Oh, sorry. So primary key of the students table is SID. And over here in enrolled, that SID column, it doesn't have to have the same name, just happens to here. But that's a foreign key that references the primary key of the students table. Okay? So that's what foreign keys are about. Now, so I showed you one case where foreign keys are helpful, which is if you're trying to add a new record to the source table, okay, the system's going to check to make sure that there's actually an existing record in the target table. Okay, that's one thing. But when else, when you're updating the database, when else might you want to check this foreign key constraint? Can you think of an update on either enrolled or students that might cause me problems for this referential integrity? Yeah? Yeah, deletion of what? Yeah, exactly. Right? Because if I delete this record here, right? Sorry, I'm not tall enough. If I delete that record there, no problem. I haven't broken anything. Okay? But if I delete this record here, right, Jones 53666, then all of a sudden, all these records over here that refer to that student are no longer valid. Yep.
In some examples, we looked at the foreign key in the other table, like that field is of a different name.
Yep. So you specify it. So the question was, in some examples, the foreign key has a different name than the field over here. And the answer is that here you say which field or which combination of fields in the source is the foreign key. And when you say references students, that assumes you're referencing the primary key. Okay? Now, I think there's a way, don't quote me on this, although I'm being taped, so I'm nervous to say this, but I think there's a way, there's also syntax that lets you say you're pointing at a different key, but I'm not 100% sure. I think some systems let you do that, some don't. But if you just say references students, that's saying by default you're referencing the primary key. That's why it's important to be careful which of your many super keys you pick as the primary key. Okay? All right, so the question now is what happens? So what should I do? So let's say somebody shows up at the database, and let's say, it's Berkeley. Jones didn't pay their bill, so we're going to delete them from the database. What should happen? What would you recommend we do? Any guesses or ideas? You're designing the database system. What should we do in that case? Yep. Yeah, you could take a hard line. You don't pay your bill, you're gone, and every record that you ever took a class here is gone. We might do that. There's a lot of people here that would be happy to do that. So that's a good answer. Anything else you could do? Yeah? Yeah, see, that's a much nicer thing you could do. You could say, well, you know what, Jones, we won't delete you yet. We'll give you another 30 days to pay your bill, so we're just not going to allow it right now. Okay, so that's another thing you could do. All right, so with foreign keys, there's a bunch of things you could do. One is exactly what you said, which is you could delete all the enrollment tuples, right? That's called a cascading delete. Another thing is you could say, you know what, exactly what you said. We're not going to allow that happen because there are these things that would be left hanging if we deleted the student record. And then there's a few other, that's called no action. And then there's other things you could do, like you can set the SID in the enrollment tables to be some default value or a null value. So those are really the choices. And when you specify the foreign key, you could say, on delete cascade, on update, no action, things like that. So that's part of the definition. Okay. All right. So we talked about domain constraints, basically just type definitions. We talked about keys and primary keys and foreign keys, right? And you can see we're putting semantics, we're putting meaning into the database, right? Into the database design, into the schema. So it turns out that SQL has some more general ways of adding constraints. So this is something called a check constraint. So if you can see here, we created the table sailors. It's got the stuff that the sailors table has. The primary key is the sailor ID. And we want to check, though, that the rating is between 1 and 10, right? So that's so you're not allowed to have a sailor whose rating is 11 or 0 or -5, okay? So this check constraint, so it's defined as part of the schema, and when you create a new sailor, the check constraints will be checked, hence the name. And if the record you're trying to insert satisfies all the constraints, the update will be allowed. If not, the system will throw an error. And likewise on update. So I create a sailor, but now I want to go in and change their rating to 11. With that constraint, the system won't let me do it. It'll throw an exception. Okay? So that's general constraints. And then you can be more complicated. So here's another example. This is on the reserves table, right, in our sailing club. And so this is basically saying, what is this one saying? So it's called, so we gave it a name, no interlake res. And basically this is saying people can reserve any boat unless the boat's name happens to be interlake. Then we won't allow it. Okay, so when we insert a new reservations record, what are we going to have to do? We're going to have to look up the boat with that boat ID, and then we're going to have to make sure that its name isn't equal to interlake. Okay? If it's not interlake, then you'll allow the reservation. If it is interlake, you won't allow the reservation. Okay? So that's what that's doing. Now, it turns out this example is a little weird in that most of the main relational database systems don't let you have a subquery in the constraint like that. So it's kind of some systems do, but a lot don't. So you just got to keep an eye on that. But conceptually, it's possible. It's just some systems don't support it. And the other thing that's kind of not super interesting, but it's good to know, is that you can name constraints. Okay, so this is saying, hey, this is a constraint that boats can't be named interlake. And the question is, why might you want to name the constraint? Some systems, I think, force you to give it a name. And the reason is because you can go back later and alter the table and say, you know what, I don't care about that constraint anymore. So you can say drop constraint. So if I decide now I want to let people have reservations on this boat, on boats named Interlake, then I could just say alter table reserves, drop constraint, no Interlake res. So that's why you need to name it. Otherwise, you'd have to delete the table and create it again. Yeah.
So, like at the first example at the top, where you check the ratings, if you wanted to also just constrain something else, would you take another check statement, like one constraint per?
Yeah, I think, I'm not sure if you could have multiple. So the question is, can you have multiple check constraints, or do you have to put it all into one big, ANDed constraint? I'm not 100% sure. So you might want to look that one up, or just type it into Postgres and see what it lets you do. Okay, but you can do it. It'll work. Conceptually, it should work either way. Yeah, and if any one constraint fails, it won't allow you to do the operation. Any other questions on this stuff? So it's not super exciting. I'll be the first person to admit it, but it's super important. It's why you want to design your database. Okay, because these are rules that are independent of any single program that anyone's going to write against the database. That's the point. And so if somebody comes by later, writes a new set of applications that accesses the database, and you want to make sure there aren't any Interlake reservations in your reserves table, that's the way to do it. Otherwise, you've got to put Post-it notes all over. When you do an update to the Interlake, to the reserves table, don't do that. It's not a scalable solution. Okay, so that's why you put it in the schema. Yeah? Oh, boy. So the constraints require the field that you're constraining on to be not null. So you're allowed to have a constraint that says not null, so you're not allowed to insert a field. If you could say, age real, not null, and then you wouldn't be allowed to insert something with a null value for age. If the field's null, I believe you just use the null semantics, right? So null, does null equal 1? And the answer to that, I think, is null. I forget. So I think you just use whatever the null semantics are. But these things you got to worry about, because if they'll bite you in strange times if you're not careful. So you have to think about how nulls work. Anything else here? Yeah. Oh, I was looking at that when I was getting ready. I mean, it's supposed to be not equal. But I'm not sure if that's actually legal SQL for not equal. Again, somebody who's got Postgres, if you're already working on your homework or something, just type that into Postgres to see if it complains. But it's supposed to be not equals. Yeah. But that one caught my eye too when I was looking. Okay. All right, good. Oh, more constraints. So you can have constraints over multiple relations. Let me just see what this one is. Okay, so let's say you wanted to have a constraint for some reason that I can't imagine, which is the number of boats plus the number of sailors has to be less than 100. Okay, you might think you could do this, right, where your check constraint says, in the sailors table, you have a check constraint that says select count SID from sailors plus select count BID from boats is less than 100, right? So it's sort of a direct translation of that English. But it turns out that not only is this kind of awkward, it's actually wrong, okay? And one of the reasons it's wrong is you can't do it. The system won't let you. You can't refer, I shouldn't say that. I'm not sure if the system will let you. That's another thing to check on Postgres. But I think there might be a problem that you can't have inside a check constraint a reference to a different table, okay? The other problem with this, so even if that was allowed, is it only checks the sailors table. So if you really wanted to implement this constraint, you'd have to have a similar check on the boats table too, right? Because if somebody adds a new boat, that could also cause a violation. And this one only gets this check only happens when somebody inserts a new sailor record. Okay, so it's awkward and wrong. And so there's these things called assertions where you can just say, check that the count of sailors and the count of boats is less than 100. And then this thing, assertions are known to refer to multiple tables, and the system's smart enough to figure out that, when somebody inserts a new sailor record or a new boat record, this thing has to be checked. Okay, so these are all details, but, important ones when you're trying to use the system. Okay, there's also a concept called triggers that just basically are sort of arbitrary statements that you get to say, on an insert, check do the following. And the following might run a little SQL program, or it might run a little user-defined function or something. There's different things you can do. So triggers are a whole other area that we're not going to get into, but they allow you to sort of call operations based on updates and deletes and inserts to the database. Those are called triggers. You might see those later in the semester. Okay. All right, so that's it about constraints. We're going to actually do two more things. One is we're going to talk about what SQL looks like when you're embedding it in other languages, just briefly. And then Joe gave me some really complicated SQL things that he wanted me to show you, and I'll show you a few of them, and I'll try not to confuse myself. So let's talk a little bit, though, about writing applications. So as you know, SQL is not a general-purpose programming language, right? It's really, what people now what's trendy. The trendy word now is it's called a DSL, a domain-specific language, right? It was a language that was developed for the purpose of querying and manipulating relational databases. It wasn't meant to be a general programming language. And so what's great about that is that because it's constrained, because you can't write, the halting problem or something in it, it's much easier to optimize, right? So you guys are going to talk about query optimization, or maybe you've talked about it a little bit. But because it's this constrained language, you can play all sorts of tricks, right? We have all these join methods. We have all these different orderings of operations. We have index. We have all these great things that we do, in the implementation of the system that we can do easily because the language is constrained. If the language was more general, it'd be hard to tell whether it was safe to do a certain trick or not. But if in a constrained, set-oriented language, a lot of things are obviously safe. You could do things in any order. And so that lets you change the order of an operation if it's going to be more efficient. If you have a general programming language that depends on order, you've got to be super careful to do that. People get PhD dissertations for coming up with optimizations like that. Okay? So it's simple, right? It's restricted, which lets us optimize it and make it run fast. But, that means it's kind of limited in what you can do. And so, the question is, well, sure, you want to write queries and stuff to your database, but what you really want to do is you want to build applications, and you want to build richer programs. And so how do you do that? And, the answer is people have tried different things. So people, including myself when I was young and naive, would try to say, okay, well, let's try to extend the semantics of the language. In fact, let's take your favorite object-oriented language and just make it a database language, right? So take Java and make it persistent, right? It's called persistent Java. I'm a little older than that. I did it with Smalltalk. It's like, it's a hard thing to do. The other thing you can do, which is what people really do, is you say, okay, well, I'm going to have an interface for embedding SQL in some more powerful language, okay? And it's a little ugly because I've got these two languages and I got to jump back and forth. But practically speaking, it works pretty well. And so that's kind of how most of this gets done. And so there's a couple things you need to do when you're embedding SQL into a language. One is you need a way of sort of moving back and forth between your query answer and your program. And so there's a notion called cursors, where you can basically, in a host language like Java or C or whatever you're doing, or PHP, you can say, open a cursor. And, the cursor is a query, right? And so the system, the way to think about it is the system goes off and runs that query and builds an answer list, okay, a list of records that are in the answer. And then what the cursor does is it just lets you iterate through the answer. So you can go, for each record in the answer to this query, do the following. If it's a student record, take out their GPA, multiply it times 7, divide it by their age, whatever you want to do. And then you can keep going. So it's an iterator. So you can basically open the cursor that gets you the answer, and then you can repeatedly fetch a record. So the cursor goes down, 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 down. Eventually you get to the last answer, and then the system says end of answer. The cursor says end of answer, and then you say, okay, I'm done. Okay, so that's how you can sort of embed iterating through a SQL query answer in a more general programming language. And so you might have a query with an order by in it because maybe you want to go from the lowest to the highest or the highest to the lowest, okay, and iterate that way. Okay. You also might have seen this limit clause. It says, well, I only want 10 answers. So here's my query, and just give me the first 10 answers. Okay, and then your cursor will have 10 answers in it, and you can just iterate through those 10. Okay? And you can also, if you think about, if you think about just having your answer as like an array, you basically just have a pointer at the current answer, and you can actually go in and update that query. So if you did like a select star on a table, and then you, in a cursor, and then you say fetch, 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 you get down to some student, and you can say, oh, you know what, I want to change the student's grade. And so you can just update the record that the cursor is currently pointing at. Okay? All right, so those are cursors. The other thing you need to be able to do is translate from variables in the host language, variables in the database, right, attributes or fields in the database into variables in the host language, right? So if I'm pulling student tuples out of my student database, I want to read those into a structure, right, a student record in my Java program or student object, right? And so there are ways to do that. There's just some syntax that you can do in the embedded language to basically pull values out from the answer into the host language, into Java or whatever you're using. Okay, so let's see. So I'll show you what one of these looks like in a second. Cursors are kind of the old way that this kind of integration was done. Now a lot of modern languages have more specific APIs that, look like you're just making calls in that language, but underneath they're actually calling out to a database. So, Ruby on Rails is a typical example of this, where, sitting underneath the Rails platform is, SQLite or some other database that you've put there. And then commands in Ruby that get translated through the Rails interface actually go out and query the database. Okay? And so some of these systems are called ORMs, or object relational mappings. And, basically they just, without you seeing it, take statements that you're asking, turn them into queries on the database, and then take the answers that are coming out of the database and turn those into objects that you can manipulate in the host language directly. So the cursor thing is kind of a more direct way of doing it, a more obvious way of doing it. But ORMs, which are sort of much more popular now, kind of hide a lot of that complexity from you. Okay? Now, by doing that, they limit what you're actually able to do, but that's the trade-off, right? Simpler, but it's less powerful. Okay. So I guess you're not going to cover ORMs much in 186 this semester, but that's a big topic in the software engineering class, 169. Okay, so you'll see it there again, and you'll see it when you start working with these systems as well. Oh boy, I thought I was going to go faster than this. I was going to tell you a little bit about the system we've built here at Berkeley called Spark. How many people have heard? Has anyone heard of Apache Spark? What's that? Oh, when was this? Oh, come on. Oh, all right. Well, so you know what Spark is. So we built Spark. It's cool. I don't think anything I'm about to tell you in the next couple slides you don't need to remember. I just thought I'd tell you because it's cool. And it's really the cutting edge. I mean, Spark SQL, which is the SQL interface in Spark, just got released, I think, for the first time like a couple months ago, like in Spark 1.2, and now it's getting updated. But maybe it was in Spark 1.0, but it's only been around like 6 months. So the way it works in Spark SQL, there's a couple different ways to do it. Some of you guys might have played around with scikit-learn or pandas or R or some statistical language. They have these things called data frames, which, if you're paying attention, you realize are pretty similar to tables in our world, right? And so Spark SQL makes that a little more that makes that tie a little more explicit. And so basically, you can basically say I've got a catalog, right, in Spark SQL that's got a bunch of Spark SQL tables, okay? And then so I'm going to open up that catalog. So I get a new SQL context. I point it at the catalog, and I point it at the database, and then say, okay, there's a thing in my catalog called users. That's a table. I want to treat that as a data frame. Okay, so that's going to be a data frame 1. And then, by the way, I want to run this query on the users table, and I want to take the result of that and store that in this host variable. Okay, so that's kind of an example of how you're tying the host language, which in this case is Scala, to the SQL system. Okay, so and there, and that's why most of these things work. You're just passing the query in as a string. Okay, then once you've done that, the data frame language lets you do things that look a lot like queries. So you could say, from the answer that I got from the result set of this SQL query, I want to keep just those objects where the age is less than 21, and I want to register that as a new table in my SQL database, right? And then once I've done that, I can just run SQL on that new table. So I'm kind of going back and forth between this data frame concept, which is a concept in Spark land, and tables, which are a concept in SQL land. Okay, and you can see I'm just going back and forth between data frames and tables. So this is all new. None of this has been released yet. It's all coming out in the next couple weeks in Spark 1.3, I believe. And then if you want, you can do things like I'm going to have a machine learning model, and then I'm going to register that as a user-defined function, and then I can. So this machine learning model is written in some language, Scala or whatever, and then I can register that as a user-defined function, and then I can call it from inside a query. So I can run a query on the users table where I'm pulling out a prediction based on the age and weight, and this prediction is actually this logistic regression model that was created in Scala. And of course, if you're doing this on Spark, it gets parallelized across the cluster. There's a lot of magic going on. But this is kind of how you're moving back and forth between. So we didn't make SQL Turing complete. We just figured out a way to embed it nicely into a language that was Turing complete. That's all. Don't worry about the syntax, but that's all that's going on here. More about data frames. Yeah, so if you don't like SQL and you like data frames, you could do this. And you could say join where group by ag, and that's my snarky comment. Some people like that better than SQL. I don't know why. And then don't ask me why we have 3 equal signs. I forget. Something with the parser. And then one other thing you can do, which is kind of fun, which is you can throw a bunch of data at the system in JSON, right? So JSON basically has the field name followed by the data, right? So there's a text, there's tags, there's a location, right? And if you throw enough data at the system, it'll look and it'll say, okay, I see what's going on here. I have a text field that's a string, and it's not allowed to be null. Every example I've seen has a text field. I've got tags, and that's going to be an array, right? Because when I saw it, in all these 3 places, it was an array, and that's not allowed to be null. And then location is a structure that's got 2 floats, a lat and a long. Okay? And it just learns that from looking at examples. And sometimes it's wrong. That's the big data world versus the traditional relational database world. Okay, but see, once you've done this, once you've shown it enough JSON data, it turns it into a relational schema. Then you can run queries on it. Okay, and if you want to add primary keys and foreign keys and all that, that's a research topic. Come talk to me. Get a PhD. It's a good thing to do. Okay. All right. Good. All right, and you can do this for other types of data too. Okay. More of an advertisement than anything. Once you've done this, it's kind of cool. You could say, all right, I'm going to pull in this table from a MySQL database that's stored at this location, right? And I'm going to create a temporary table called users. And then I'm going to read in this JSON file into a table called logs. And then I'm going to do joins of the user table and the logs. So I'm going to join MySQL data with JSON data just by running SQL. So anyway, this is where the world's going. So, there used to be, SQL database, cursors, and so on. Then there were object relational mappings that kind of tried to hide a lot of the SQL stuff under the covers, so you never saw it. This is an intermediate step, which a lot of people like, which is I'm going to expose the SQL, but I'm going to make it as easy as possible to go back and forth between all the different ways I like to think about the data. JSON, data frames, SQL tables, whatever. So that's just an idea of where things are going. So you can now forget all of that, but I just wanted to kind of make it a little more specific. Yeah. Okay. So I want to do. It says summary, but we're not done yet, and we're going to get to the part where I'm going to embarrass myself a little if I haven't already. But let me just wrap this part up. So the whole point of the relational model is you get these well-defined query semantics. For a given database, for a given query, there's one correct answer, and the system will give it to you. SQL follows the relational model that you've been studying, but it's a little, because of practicality, it's not quite as pure. So, you learned about relations as being sets. Well, SQL supports multi-sets, right? And you've learned about, sets. With sets, order doesn't matter. Well, one of the main things you do in SQL is sort things, right? Because that's what you need when you're building real applications. So the idea behind SQL is to try to stay as close as possible to the pure relational model and then extend it where you really need to for functionality. And then the fun part, as you already have seen, is there's lots of ways to write a query, which is not really a good thing, but that's just the reality of it. And the good news is it's up to the database system, the underlying software, to say, okay, given a query, how do I turn that into something that runs quickly? And one way it's going to do it, by the way, is to do some pattern matching, and I'll show you this in a second, where it says, hey, you wrote the query this way as a nested loop, but I know I can turn it into a join. And once I turn it into a join, I can do all my favorite, hash join and other algorithms to it. So I'm going to, without telling you, I'm going to convert the query you wrote into one that I'm guaranteed is going to give you the exact same answer, but that I can run faster. Okay, and that's a lot of the fun. If you like building these systems, that's where a lot of the fun is. Okay, and that's what you'll be studying in a couple weeks, I think. All right, and then the other thing that's not on the summary, but should be, because we just talked about it, is that, the schema lets you describe all these things about truth about the database that have to persist, independently of any individual application or program that somebody writes. So to the extent possible, you pour those rules, those constraints into the schema. That way, it makes it easier for application developers to write code and know that they're not going to be able to corrupt the database. That's the idea of constraints. So we'll add that too. Okay, getting serious. All right, so there's two queries in here. I'm going to do the first one. I'm not going to do the second one. But maybe I'll show it to you. So, okay, so the first one is kind of cute. It's a median query, right? So you know that if you want to get the mean of a set of numbers in SQL, how do you do that? Yeah, use the average aggregate function, right? That's great. But you might not want the mean. You might want the median. So how do you do that? Well, remember what the median is. So if you take all your values and you sort them from smallest to biggest, the one in the middle is the median. Okay, so half the value, half minus one of the values have value less than that, and half minus one have values more than that. And if you have an even number, there isn't of items, there isn't one in the middle, and so you got to pick one. So we're going to pick, of the two middle ones, we'll pick the lower one. That's our definition of median. Okay, and that seems like a detail, but when you look at the SQL queries, you'll see it's an important detail. Okay, now why might you want to do median, right? So this is less about databases and more about statistics. There's a couple reasons. So here's a question. Let's say you wanted the mean to be 1 million, right? Let's say, you were trying to, corrupt somebody's data analysis, and you knew that they were computing means, and you wanted them to get the answer 1 million when they ran their query. How many records would you have to change or add to the database to make that happen? Yeah, one. It might be a really big one, but just one. Okay? If you wanted the median to be 1 million, how many records would you have? It probably says it up there. Oh no, it doesn't say it up there. So how many records do you have to change if you want to fix the median to a certain value? Yeah? Yeah, at least half. Right? So it's a big difference, right? You got 1 billion records. The mean you can change just by doing one insert. The median, if you really want to make it a particular value, you got to mess with 500 million records. Okay, so that's called a robust statistic, right? Any one change could have a huge impact on the median. On the mean. In fact, you can't really say how big, but on the median, it can have only a very small change. Okay, and so it's important for medians are important because a lot of times you're doing analysis over data that's dirty, and one bad value could really screw up the mean, but one bad value isn't really going to mess up your median too much. And also just for outliers. Sometimes you're trying to compute a statistic about, like, say, typical one is, what's the average income of an American family? Well, the average is skewed by, the 100 people that are, at the top, 0.0001%, okay, who are just making crazy amounts of money, and that impacts the mean for everybody. Whereas the median, basically they don't have much of an impact. And so when you're thinking about, doing statistics over data that has this kind of wide spreads, and in particular a lot of outliers like that, median's a much better statistic. That's why when people quote, statistics about household income, they typically say median. They don't say average. Okay, so that's why median's important. You'd think there would be a median aggregate in SQL, but there might be now. But in SQL 92, there isn't. Okay, and so the question is, how do you do it? So before I uncover this, okay, so this is, I spent some time on the phone with Joe about this a little earlier. So and these slides are a little different than the ones you have. So this example works for when you have an odd number of things, okay, when there is a middle value. Okay, so we'll start there. So if I wanted to write a query, so I've got this list of numbers T, right, a record of integers T, right, with some field C, right. How do I think about computing the median of this relation T? I'm looking for the C value, right? So I'm sorry, this is underspecified. So T has one field, it's C, and let's say it's an integer. Okay? So if I want to find the median value of C in this whole T relation, what can you tell me about that value C that I'm going to find? What can you tell me about it? Yeah. Exactly. This is why SQL is so great, right? Because it's exactly that. You want to find the value of C in this relation T that's got exactly the same number of things that are bigger than it as it has of things that are smaller than it, right? So how do you write that in SQL? Well, you say, okay, here's a number of things that are smaller than C, right? So I'm going to select, I'm going to use T again, and I'm going to say, all right, count how many things in this other copy of T that are less than this particular value of C for this tuple from T. Those are the ones that are less, and I want that to be equal to the number of things that are bigger than that in that same relation. Okay, so that's how I do it. As long as I have an odd number, right? See, that's why that's why it's important that it's an odd number. Okay, and I'll leave it as an exercise to you guys to think about how to do it if there's an even number, and then how to do it if you're not sure which there is. Okay, all right. So this works. It's exactly what you said. Just instead of translated from English, it's translated from English into SQL. Some of us think in SQL. So, okay. So, is there anything? So it's correct. So I think, unless I screwed it up. Yeah.
What if we have duplicates? So we have like number 5 in there 10 times. We might end up with the median being 5, but number of entries that are less than or greater than that entry is different.
Yeah, you are really smart. So about 5 minutes before I left my office, I removed the less than and equal. But I did it for a reason. I'm trying to remember why. So this used to say less than or equal. I think I'm going to change it back. I forget why I changed that. Okay, so let's do that. And this used to say greater than or equal. Yeah, I was thinking about that on the way down. Okay, so anything else? And double check, so please, for you in TV land there, double check, make sure I get it right. I might have screwed it up. Okay, it's not my slides. I changed them. I'm sorry. I'm sorry, Joe, I changed your slides. Okay. But let's assume it's correct. So, is there anything that sort of offends you about this program or sort of makes you uneasy? Yep. You're going to correct it again? No. Oh, I thought you were telling me. Okay, well, what offends me about it is it's forcing me to do nested loop evaluation, right? This is basically, if you think about how this is going to work, it's going to say for every record in T, look at the value for the C field, and then count everything and then count everything again. And I got no choice. I'm going to go record by record by record through T to do it. I'm forced to do nested loops, which, as you guys, I think, have already learned, is not always the best way to do things. Okay, so great. So what could I do? Well, you could do something like this, and I think I got this one right. I might have done that less than or equal thing wrong again. Not sure. But you can basically say, do a self-join. So join T with itself, right? So pair up every combination of take T and match it up with every other record in T, okay? And then you could group by this C value. So, you take one of them, you group by it, and then for each group, you want the one where the sum of, I might have screwed this up again, the sum of things that are bigger than it are equal to half the number of things. I'm sorry, the count, this is a count. So the count of the number of things that are bigger than this value of C is equal to half the number of records in T. Okay? I think I screwed that one up too. But you get the idea. It might be off by one. Okay? So what this one's trying to do is allow you now, why could this be faster? Well, because now I don't have this nested loop operation, right? I'm doing the self-join here, and when I do the self-join, I can play any trick I want. I can do block nested loop. If it makes sense, I can do hash joins. In this case, it doesn't because I don't have an equality predicate. But I can do at least block-level things, which is probably going to be a lot faster. You guys might have called it chunk-oriented nested loops or something like that. But the bottom line is by turning it into a join instead of a nested loop, you're giving the optimizer freedom to do something smarter underneath. Okay? So does that make sense? And again, check whether I'm off by one. I might miss one here. Okay. So that's if it's odd cardinality. Now, the one I was supposed to show you is this one here. And this is why I did the simpler ones first. If you don't want to restrict yourself to odd cardinality, right? So you want to be able to handle this on relations that have either an odd number of items in them or an even number of items in it. Then you can write that same thing I just said this way. And I'm going to let you guys kind of go through this yourself because I had to a little bit. But the bottom line is you can think about this as being the ceiling of the number of the cardinality of T divided by 2, right? So the ceiling of the cardinality of T divided by 2. And then this one here is the floor of n divided by 2 plus 1. And what you'll see is that for odd numbers of for relations that have odd numbers, odd cardinalities, these two values are the same. And for relations that have even cardinality, this one is one bigger than that. Okay? So I'm going to let you guys work this out because I've already embarrassed myself enough. Okay, but I worked through it, and this one works. The ones I messed with while I was sitting in a talk that I should have been listening to, I might have screwed those up, I admit it. Okay. All right, so again, so there's two lessons here. One is you should stare at this for a while and run it in Postgres and see why it works. Okay? And then the second thing is to think about, we had this thing here, that was a lot simpler, but kind of tied the hands of the query optimizer. It said, thou must do nested loops, record-oriented nested loops. And here we turned it into a self-join, which just opens up a lot more options for the execution engine. Okay? All right, so that's one thing I was asked to show you. So that's median. And again, remember where we started. It started with this really simple statement is I want to find the record where, the number of things bigger than it and the number of things less than it are the same. Okay? That's what we did. Yeah? Yeah, so this is a self-join. So we basically took the table T and we joined it with itself. C is the one field, so so T has one field in it, and that field is C. Yeah. So there's x dot c, which is, the c attribute of the x instance of the table, and y dot c is the c attribute of the y instance of the table. Okay, but it's self-joined. Most nasty, a lot of nasty queries in SQL tend to be self-joins. Okay, and you'll see in a second we're going to actually take this idea of a self-join and exploit it even more. Okay, this is another thing that I'm going to let you puzzle through, but SQL more recently being about 10 or 15 years ago, added this notion of window functions, where window functions have built into them ordering. So what this is saying is, I've got my so I've got a table numbers, and what I want to do is I want to create a view over that table where the records in that view consist of three fields. The first field is this field X that comes straight from the records of numbers. And then this magic is kind of cool. This says order X ascending, right? So take the entire numbers relation, sort it from lowest to highest, and then tell me, return which position this particular value of X is at. Okay, and then this one says do the same thing except order it from highest to lowest, and then return the position there. So basically, each record of two counters is a value from the table numbers, plus its position in the ascending order, and that's the second field, and the third field is position in the descending order. Okay, and then given that stuff makes sense. You can write this query over this view that basically computes the median that way. Okay, so find all the rows where this middle field is either right where the ascending position is the same as either the descending position, or one less than the descending position, or one more than the descending position. Right. So take all the values for X where that's true, and then take their mean. Okay, the integer mean, and then that gives you the median. Okay, so I worked through this on a couple examples that seemed to work. Again, fire up Postgres, try it out, see if it works. Okay, but this is just another Postgres as of 9.3 does have window functions. Okay, all right, and supposedly it handles an even number of items. Okay, one last thing that Professor Hellestein wanted me to make sure I showed you, and then we'll wrap up, is another thing you can do with SQL is, some interesting graph algorithms. And so if you think about something like a social network where you have people that are friends with other people, and you want to, build that out, or you can think about the web where, one web page references another web page and so on. You want to compute over that. These are all graph problems and all things that you might want to do on graphs that are pretty large, like all the people in the world or all the web pages in the world. So this is an example where you might do something with social networks. And let's say you have this table friends where you have the ID of a person as the source of the relationship, the ID of the person as the destination of the relationship. So somebody, the from person is friends with the to person. Okay. Since a certain time, you only want each one of those in there once, right? And then these two IDs are foreign keys referencing users, so they have to be people that exist in the users, records that exist in the users table. Okay, and then I want to make sure in my friends table I only have records where the from ID is smaller than the to ID. So I don't have, so if A is friends with B and B is friends with A, they're only in that table once, right? Because I'll have A and B, but I won't have B and A. That's what this check constraint does. Okay? Given that, you say, okay, well, what if I wanted to reconstruct the two-way relationships? That's what this both friends view does. Okay, so it takes every record that's in this table, and then it unions it with all the records that you would get from flipping those relationships. Okay, this stuff is weird. I'm glad I'm running out of time. Okay, but that's what that's what both friends does. Okay? All right, good. Now, given both friends, you might want to ask the question, right? You all heard about the 6 degrees of separation, right? That, on average in the U.S. in 1950, whenever they did the experiment, you could get from one random person to another random person on average 600, with on average 6 hops. That's called the 6 degrees of separation. Nowadays in the internet, it's gone down to 3 or 4 or something like that. But there's a certain number of hops you have to go through to get from one random person to another in this type of a social network. So if you wanted to do that 6 degrees of separation, and I believe this is something that's important for your homework, which is why Professor Hellerstein wanted me to go over it quickly. If you wanted to compute those 6 degrees, so for a given from ID, who are all the people that are within 6 degrees, that are 6 degrees away, this is how you do it. You take that both friends, and you join it, you join it, you join it, you join it. So you self-join it 5 times, and then you just make sure that, this from is connected to this 2, which is connected to this from, which is connected to this 2, and so on. Okay, and you can build out strings of 6-degree hops using that query. Okay, and I believe this is relevant to your to your homework. Okay, so take a look at that. There's another query in here that, if you want to have fun, ask your GSIs to explain it in section. I looked at it. I had no idea what was going on. Or you could ask Professor Hellerstein to explain it in the next lecture. So one announcement, which is there's a survey out on Piazza, and please fill it in so people know how we're doing. And thanks for your patience, and see you around. Thank you.